Hello, everybody. Today I'm going to come to you with yet another question. I'm going to ask, how is a small biological microscope, like the one I'm holding in my hands here, similar to a transmission electron microscope, which utilizes a very powerful electron beam to look at specimens? And think about it a little bit and watch the next lecture. All right, everybody. We've gotten to the point in this course where we're talking about transmission electron microscopy. And the picture you have in front of you is a transmission electron micrograph of copper. I've kind of cut my face out of this lecture this time because I have a lot of pictures that I want to be sure I just don't cut them out. And I think most of you know what I look like. But what we have here is we have copper. We have kind of two bits of information here. So we have our bright field image and we have our diffraction pattern. And so we take advantage of electron diffraction a lot of times when we do transmission electron microscopy. And using these two bits of information together, we can learn a lot about material. And the kind of the microstructural feature that was of great interest during this body of work. So this is from my own thesis from many years ago. I looked at hypervelocity impacts of impact craters, and I don't know why I had the micrograph disappear, but I had these impact craters, and I was looking at the microstructural features that evolved as a result of hypervelocity impact. This body of research is still done by other people across the country, particularly NASA, and it has implications for spacecraft because there's a lot of space debris. And one of the most read books I read during my thesis was a book called Orbital Debris, A Technical Assessment. And so this has some, I guess, direct impact, I guess, on aerospace. Well, anyway, I was looking at the microstructural features that occurred in these hypervelocity impact craters, and the microstructural feature of interest is this. And one thing I want to kind of point out is this is purely contrast-driven analysis. Even looking at a diffraction pattern in this instance is really just looking at the differences between black and white. And here we're looking at differences between black and white. Kind of some other things I want to say. Sorry for stuttering a little bit. Hand-drawn micrographs, so my advisor was a stickler on stuff like that. So all my micrographs in the original state were a centimeter because I used 1 cm equals 1 over mag times 10 to the 4th micron, as we talked about with optical microscopy. So I have my handmade micrographs here. This is a hand-developed picture. And so we had a negative that we then had to go put on a projection device and project the image off of our negative onto some photographic paper. And so there was kind of a double photographic process that happened. So we had a real camera that gave negatives, none of this digital stuff we have today. And CCD is pretty commonly used, and so is a CMOS image sensor. So both of those imaging technologies we've talked about before are currently used on modern transmission electron micrographs. Developing photography is something that grad students generally don't do much of these days unless it's a personal hobby. Well, anyway, microstructural feature, these things called microbands is what they're called. They're dislocation structures. The diffraction pattern here, I'm indicating a 15-degree misorientation with the parent lattice, and that's kind of how you tell that this is indeed a microband. It's this 15-degree characteristic misorientation angle here. And let's go to the next slide. So talking about how they're formed, you have some shear going on as a result of the hypervelocity impact we see in the craters. You start forming dislocations, okay? So we learned that very young, very early on in our metallurgy curriculum, that when you start bending metal and deforming metal, you start forming dislocations. The hypervelocity aspect of this and the shock wave that occurs here creates kind of an order to these dislocations. I'm going to explain this really fast without other figures. And we start having some ordering of the dislocations. We end up with these Cottrell Lomer locks, and secondary slip starts to form. So these dislocations start forming on the secondary slip planes instead of just 1, 1, 1. Okay, and so this secondary slip is what then leads to the formation of the microbands, characterized by this most orientation angle of 15 degrees. So hopefully that's a quick explanation. Making of the specimens was very tedious. So again, we have the different versions of impact craters. So we shot tungsten carbide into copper targets at different speeds. I then had to extract material to look at with the TEM, and I'm sharing this because I want to kind of convey that the specimen preparation, extremely tedious, specimen size, very small. And so we're talking about discs on the order of 2 to 3 millimeters in diameter. And so here I'm kind of depicting 3 millimeters for this little square. I cut out a small column of material. This was with a high precision diamond blade from different radii of the crater. So I'm showing just below the impact. I also took some radial specimens, and it was not easy. This is a hand-drawn schematic from my youth, actually. I then embedded the so-called crater material into epoxy, and I used a steel ring to kind of protect the material, because it was actually copper. And then I cut very thin slivers, roughly 100 to 200 microns in thickness, and actually thinned that down even further. And we'll talk a little bit more about specimen preparation techniques for electron or transmission electron microscopy before this section of the course is done. Throwing this in here at the beginning just to show that TEM, specimen prep, very tedious. A lot of people detract from the power of TEM microanalysis, and they detract from it because the sample size is so small. And so if you start doing things like looking at dislocation density based on TEM micrographs, because if you remember the concept of the modified Hall-Petch equation, where Hall-Petch equation is generally driven by grain size, you can add on a term to the Hall-Petch equation to incorporate the strengthening effect of dislocations and precipitates and anything else, okay? And particularly the dislocations, because really a TEM is the only thing that you can use to see dislocations, maybe an AFM as well, but you need atomic resolution to actually see dislocations. If you're making these claims about the strength of material based on a specimen that's this small, sometimes people balk at that a little bit. So just be ready for that in your careers and stuff like that. I myself have had many arguments with individuals, and they say you need a statistical data set, and it's kind of two different points of view. And here's the analogy I tend to use. Okay, so if I walk up to a river and stick my hand in there and I catch a fish within like 5 seconds, I'm going to say, man, this river's full of fish. Okay, well, in a manufacturing environment and even some experimental environments and research, someone will tell you, no, there's not a lot of fish in there. You were just lucky. Okay, you got to try 100 times. Okay, and so these are kind of the arguments that you get into sometimes with people when you're doing this kind of tedious, kind of high precision microscopy, like transmission electron microscopy. And again, specimen size is very small. If I make 10 specimens, maybe 1 or 2 come out. So you have to almost be lucky sometimes to get a good specimen. And so very hard to do. I've made specimens with various techniques for transmission microscopy. Kind of showing this slide again. And we talked about this when we looked at SEM, so electron microscopy history. So the big kind of breakthrough that led to some of this stuff was de Broglie, and 1924 kind of figured out the wave-particle duality of the electron. We've gone through this derivation before. I'm not going to do it again. If you want to see the derivation, look back at the SEM videos, the SEM lectures. But lambda equals h over mv, or lambda equals h over momentum. Okay, and this is probably the wrong subscript. It should have been a V. Maybe it's just the font. But this is momentum, and hopefully you guys have that ingrained in your brain right now. Max Knoll and Ernst Ruschka, 1931. These guys were the Electron Research Group, the first electron image, and I often wondered where they were from. And I found a display at a research center a little while ago that kind of told me where it was from. So the first commercially available, where they're from, sorry. The first commercially available TEM was 1935. World War II stalled the development of SEM, and a lot of the electron optics used for an SEM relied upon the television, basically. And we've kind of talked about Philo Farnsworth and that kind of thing. And this is my statement, my claim to fame. I'll have it engraved on my gravestone, perhaps. Accelerating electrons to a column is the basis of electron microscopy. Kind of a lame statement. Maybe I'll find something better. Here's the napkin that Knoll and Ruschka used to design their TEM. Actually, I don't recall where I found this, but this is actually an early schematic of the TEM, basically. And here's me standing in front of an early TEM with our illustrious department chair. This is a research center down in Chihuahua, Mexico, and so they have this on display. And this is directly related to this, basically. So this is a Siemens TEM microscope. And so Knoll and Ruschka were in Germany. Siemens is, of course, a German company. At one point in time, I worked for a subsidiary of Siemens in my life. And very interesting. And you can kind of see it's a little tall. I don't know if that's a good scale. And anyway, so there is this display text next to it. And so this was kind of cool. So it's a Siemens Elimskop 1A. And so it's basically saying these German scientists here, Ruschka and Knoll. So I learned that they were German by reading this. I never knew 100% for sure until I read this. And this was actually kind of cool because this is basically the first commercially available transmission electron microscope. And they had a model apparently at NMSU, so up the road from UTEP. And then NMSU donated it to these folks. This is SIMAV. It's a Conisset Research Center. Very, very cool, very, very awesome place. I always am amazed at the history of the characterization equipment we use. And it was really, really cool seeing an old one like this, and actually the first one. And really doesn't look much different than the TEMs we use today. So Knoll and Ruschka, German scientists, Siemens, the first company to make a transmission electron microscope. And I want to kind of throw this out here right quick. TEMs are cool, and they allow for the collecting of data generated in real space and reciprocal space. And I didn't use this terminology purposely when I talked about the microband image. Again, this is a bright field image, and so this is real space, and this is reciprocal space. And reciprocal space is also called K-space. And we'll hear that time and time again. It becomes more pertinent when we talk about kind of the quantum explanation of X-ray diffraction. But this is kind of cool. And so learning how to interpret these micrographs is very, very important. Again, this is all kind of hand developed. These are dynamically recrystallized grains in copper. And this again is from the same project related to hypervelocity impact. I know that these rings here are telling me that they're dynamically recrystallized grains. Extremely polycrystalline, you see a bunch. And I know a little bit about the process history. Okay, so I know that the material was subjected to a lot of material flow. If you go back here, you can actually see it. You know, this used to be a solid block, and here's the remnant of the crater at the bottom. We have these kind of petals that form at the top. And I've argued with people in my past, and several people told me that it melts. No, it doesn't melt. This is a solid state deformation process. So the forming of these kind of petal looking things at the edge of the crater, and this is a cross section, so I cut it in half on this plane here, is all solid state material flow. And to facilitate solid state material flow, you need what? Dynamic recrystallization. So we see these nice dynamically recrystallized grains. You can figure out the thickness of your specimen by counting these fringes, and we'll get to that later in this section. But real space is your image. Reciprocal space is your diffraction pattern. Reciprocal space, also called K-space. Using real space and reciprocal space is really, really important. Okay, so at the very, very beginning of the lecture, and I'm sorry for going back and forth so much, and hopefully you're not watching this lecture at double speed or something, but we used our reciprocal space information and the misorientation. If I draw a line here from the center of the transmitted spot to here, and the center of the transmitted spot to here, and it's a little blurry, so this might not be the best one to do it on. I measure the angle between the two, and it's 15 degrees. Okay, that's how I identify this is a microband, and that's using reciprocal space in conjunction with real space to help in your characterization process. Okay, so we know a little bit about microbands. We know this 15-degree misorientation is a characteristic angle, so I know that these are microbands because the diffraction pattern tells me so. Similar thing here, I'm looking at these really small grains. I know it's polycrystalline. I know a little bit about the material processing history. I see this micrograph knowing that there was some material flow, dynamic recrystallization. So I'm using, again, reciprocal space to help me interpret my real space image. Very, very important. Again, looking at differences in black and white. Very, very powerful is contrast. Almost Yoda'd it there. Yoda. All right, so this is a twin, and kind of, you know, my little schematic of a twin. It's a fault, so A, B, C, B, A. You kind of change your stacking sequence of your atoms. The other reason I know it's a twin and not, you know, a Sharpie mark or something, or something else, some other kind of fault, is it makes roughly 90-degree angle. So my real space image, if I draw it out and I draw a line tangentially through my diffraction pattern here, I get roughly a 90-degree angle. And it's very, very important to kind of make sure the orientation of your diffraction pattern is consistent with the orientation of your image, or else doing analysis like this becomes really, really hard. And anyway, again, using reciprocal space in conjunction with real space to help interpret what's going on, basically. Okay, using the two bits of information together, very, very powerful. It's also an image. So diffraction in this instance is image-based versus spectra-based. Okay, so a little bit different than XRD. All right. Kind of looking at some real space images, and this is actually kind of cool. So this is off of our TEM in the department, and we see 2 grains actually. And so if you look here, you can see the atoms are oriented in this direction, and we can actually calculate the misorientation angle between the two. The atoms oriented this direction here. So these are actually 2 grains. And this is a grain boundary, and maybe there's some preferential etching or something like that. This was done at a facility in Albuquerque called SINT, and this young person was on her PhD dissertation back in 2015, and she was doing thin film work, and she got some very beautiful TEM imaging. And we have here some faults. We know they're not twins because the diffraction pattern is not making a 90-degree angle with them, so it's some other type of fault. What's kind of cool is you see the interface between the silicon and the zinc telluride film, and you see here dislocations. And so in electronic materials, I kind of talk about how dislocations facilitate lattice mismatch. So dislocations are a good thing. Sometimes they're a bad thing, but sometimes they're a good thing. This micrograph is super cool. You can kind of see a diffusion zone here. What's really neat is SiO2 is, of course, amorphous. So we see amorphicity on a TEM micrograph. So you can see the orderedness, if you will, of this CAD telluride and this germanium. You can actually see the rows of atoms, but here you see atoms, but there's no real order to them. So silicon dioxide amorphous, CAD telluride crystalline, germanium, of course, crystalline. And so this is really cool. All seen with the TEM. I kind of circled off this little square to kind of give credit to Rizbe. Very, very talented young person. Anywho, power of TEM, real space images alone tell you some cool stuff. real space images with reciprocal space diffraction patterns tell you even more stuff. It's really cool. Seeing amorphicity with my eyes, that's really neat. And crystal structure, dislocations. I mean, it's just really cool. I love electron microscopy. It's just awesome. So similarities to scanning electron microscopy: you have an electron gun, you have a column, and it operates in a vacuum, very, very high vacuum. Similarities to optical microscopy, and I meant to have a picture here of a biological scope, but if you look at this schematic that our textbook Brandon and Kaplan gives us, we have our electron gun, different apertures where our specimen lives, some other apertures and lenses, actually, excuse me, magnetic lenses, and our recording plane. So a TEM is basically just an inverted biological optical microscope. And in fact, the design of the TEM was based on a biological optical microscope, because that's all these folks had to go on. Okay, so the sources at the top in this instance, they're blasting the light through your specimen stage, and you have two different lenses, and you have your recording plane. But think of a biological microscope. All right, through some creative editing, I've added in the biological microscope so it's inverted. So we have our light source, we have some sort of condenser for the light, if you want to use your imagination. We have where our specimen is, we have our objective lens, and this final imaging system, and observation and recording system, so I can put a camera right here. So a TEM similar to an inverted biological optical microscope. Why? Because that's pretty much what the designers of a TEM had to go on. There are TEMs that illuminate going the other way, and I always thought that was kind of strange. But anyway, people dare to be different, more power to them. Kind of a reminder of the electron guns. So we talk about the vacuum column, and here's where the electron gun is on a TEM. And let me get a laser pointer. Here's where the electron gun is on the TEM. The electron guns, tungsten hairpin filament, lab 6 tip, and field emission tip. Okay, and just kind of a reminder, we talked a little bit more detail about electron guns on scanning electron microscopy. This is missing Schottky, and I was realizing in my brain I don't know if they actually make Schottky TEMs, and I'm almost thinking that no one does. And but I challenge you to Google it and find out. So explore a little bit, see if there's a Schottky based TEM, and I'm thinking there may not be. So anywho, just food for thought there. I like this schematic, and I think this is a Hitachi or Joel. I don't remember. I'm pretty sure it's Hitachi. No, it's probably Joel. If you look really close, you can see that that's a Joel microscope. So this is Joel. So another big company, Japan Electron Optics Lab, Joel. Hitachi's another one, FEI, another maker of TEMs. And I don't know if TestScan and Zeiss make TEMs, to be honest with you, but I know for sure Japan Electron Optics Lab, Joel, Hitachi, and FEI, which was formerly Philips, which I think Philips was actually owned by Siemens. So there's some history there. FEI, I think you're buying history if you buy an FEI, a long heritage in electron microscopes. I may be wrong, but anyway, conventional TEM, and I generally refer to these as biological TEMs. And actually, biological TEMs tend to cut off at 100 kilovolts, and you can run biological TEMs at like 80 kilovolts. So it makes it useful for polymeric specimens as well as biological specimens, obviously, like tissue and stuff like that. But according to this slide, conventional TEMs 100 to 200 kilovolts. High voltage TEM, or intermediate high voltage TEM, according to this slide, is 300 to 500 kilovolts. So the TEM we have on campus runs at a maximum accelerating voltage of 300 kilovolts. The chemistry department has a Joel. It's a cryo TEM, and it also operates at 300 kilovolts maximum accelerated potential. You can always run it lower. Ultra high voltage TEM, 1,000 kilovolts. That's pretty dang high. And so this is a big one. So 1.3 megavolts. Okay, so 1,000 kilovolts is a megavolt, and this is huge. Here's your observation area, and here's the gun, and it's like a nuclear reactor, I think was the design. Really very interesting. I may want to look into that a little bit more. I don't think this is using a tungsten hairpin in the electron gun. They have the scientists here as a reference in terms of size, and so you can tell this is pretty big. And I used to have a picture and I've lost it, and I guess I could Google it and find it again of someone actually using one of these. Very, very impressive. But they range in scale. If you remember wavelength, the higher the accelerating voltage, the shorter the wavelength. The shorter the wavelength, the smaller thing you can see. And I'll have a supplemental video for you to watch on basically the development of a very, very awesome TEM. Speaking of wavelength, so we're starting off, we're calling SEM wavelength, okay? And TEM wavelength is we kind of start again with de Broglie, just like we did with SEM. And so we kind of start from the equation of the SEM wavelength. So EV equals mv squared over 2, so 1/2 mv squared. Okay, so E is the charge of the electron, this V is the voltage, this is the velocity, and M is the mass of the electron. And so V, if you recall, the speed equals the square root, I'm trying to do this without writing it, and it may be my folly, is 2 EV over M. Okay, so there's a direct proportionality, so it's a square root. But still, the bigger the voltage, the faster you're going to go. Okay, so the bigger the voltage, the faster you're going to go. And so we're operating at really, really high voltages. So if you go back and look here, we're always, in most cases, okay, at least, the very least, an order of magnitude higher voltage than a SEM. Okay, so SEMs typically peak out at 30 kilovolts. TEMs generally started around the 100 kilovolt, maybe 80 kilovolt, but you know, a little bit of hand waving, we're at least an order of magnitude higher voltage, so we're going to be a lot faster. So when you make the equation for the TEM wavelength now, you have to incorporate a relativistic term. So this 2mc squared, or this whole thing, I guess, is a relativistic term. This is a lot of numbers to punch, and so you can write it in terms of lambda equals hc over the square root of voltage. The units don't really cancel out. It's another one of those approximations. But lambda equals 12.4 over the square root of voltage, and that's in angstroms. Okay, simple approximation. You get pretty darn close. One thing I always want to draw people's attention to is within Brandon and Kaplan. And did I copy that by accident? No, I didn't. Okay, within Brandon and Kaplan, this book is wrong. Okay, on page 185 within the text talking about TEM wavelength. If you go to the back and look at the appendix, okay, relativistic electron wavelengths, okay, so this means fast. So starting at about the 100 kilovolt range, we have to start incorporating this relativistic term, C celeritas. They probably shouldn't have used the big C, right? Anyway, this equation in the back of the book is right on page 521. So I always want to draw your attention. And it's nice, they have a table so you don't even have to work it out. So this actually is giving it to you in nanometers. Be careful with units always. This approximation's for angstroms. It's an old approximation, old folks like me, before the nanometer was invented. Wink, wink, nudge, nudge. Anyway, when we talked about the electron beam interaction for an SEM, this is what we cared about. So backscattered electrons, visible photons. We didn't really talk about visible photons all that much. Auger electrons, secondary electrons, and X-rays. So this is generally what we care about. When we talk about a TEM now, we have a very, very thin specimen. So it's not like XRD in that sense, but it is like XRD when we talk about a diffracted beam. So we actually care about diffraction here. Transmitted electron beam, so the beam goes through the material. We get our image, diffracted electron beam, we get our diffraction pattern somewhere over here. Through the magic of electron optics, we can actually see diffraction patterns, and we'll talk about that. It's a series of apertures. We'll talk about that when we look a little bit more deeper at how the machine works. Kind of a little tidbit, or kind of a little foray into how the machine works. We can look at this schematic. Got this from Microscope. Again, here's a column, Phillips. Now I think they sell them under the FEI brand. FEI is field, electron, and ion, I believe, is what FEI stands for. Maybe I should make a little contest or something. I don't know. It's interesting. This schematic shows 2 condenser apertures, so may be adjusted by user depending on TEM type. So most TEMs I've worked with personally only have 1 adjustable condenser aperture and 1 objective aperture in the selected area. So it's cos, like cosine. So that's how you kind of remember the order of apertures. Condenser, objective, selected, cosine. Your specimen goes here after your condenser aperture. So you condense the beam, blasts through the specimen, hits your objective aperture. If you insert your selected area aperture, you're looking at a diffraction pattern. If you take your selected area aperture out, you're looking at your bright field image. Okay. What's really kind of cool, and we'll talk about it more detail, you have a series of apertures. Okay, so when you take your selected area aperture out, you're going to look at the image generated by this beam. So this is bright field. You can use your aperture to image this beam, and this would be dark field. And we're going to talk about it in a little bit more detail later. I just thought I'd throw that in there now. You also give off X-rays. Don't want to forget that. So you can do EDS on a TEM. Reciprocal lattice. Okay, so basically this is the premise upon which at least diffraction patterns work. I oftentimes debate if I should talk about it on X-ray diffraction or save it for electron diffraction, and in most cases I save it for electron diffraction. But it's basically a construct to help us interpret diffraction patterns. And so the reciprocal lattice lies in reciprocal space. I've said this before already. It's also known as K space because this is the K vector. And we'll see a different way to describe Bragg's law where we care about the K vector. So K space, reciprocal space, the same thing. This is your reciprocal lattice vector, and here's your diffraction spot. This is the incoming beam. Let's just say this is your specimen, and this is the transmitted beam. Okay, kind of a poor schematic. The Etoile sphere is the reflection sphere, and that's where diffraction patterns live, on the Etoile sphere. And the general radius of the Etoile sphere is 1 over lambda. The limiting radius is basically the limit to diffraction, and this is a little incorrect. All right, some creative editing. Now it's correct. So if you remember, the limit to diffraction is half the wavelength. So the radius of our limiting sphere has to be half the wavelength, lambda over 2. Okay, and very, very important, when the reciprocal lattice vector G intersects the diffracted K vector K, you get a diffraction spot. An angel gets its wings. No, you get a diffraction spot. And so again, this is the K vector. This is the reciprocal lattice vector denoted as G. It has different denotations depending on who wrote the text. I learned it as G. I left K out of both of these diagrams. I apologize. Oh, there we go. Denoted as K or K. Okay, so K vector or K with a little squiggly line underneath. So this is the K vector. Okay, and again, when the K vector intersects the G vector, you get a diffraction spot. So K vector, G vector. G vector is the reciprocal lattice vector. I'm saying a lot of things about vectors. Don't get them confused. Just know that when G intersects with K, you get a spot. We'll see it again. All right, so how do we construct reciprocal lattice space? We're dealing with vectors. So we're dealing with a reciprocal lattice vector, and we're dealing with the K vector. So vectors are pretty much how we make this construct. And the following explanation I got, or I learned from reading Cullity, the XRD book, and it applies here. And I know some of you have access to a copy of Cullity's book. If you find this explanation a bit lacking, feel free to look elsewhere. But let's move on. So basic vector stuff. So I have two angles A and B. I mean vectors A and vector B. They're separated by angle alpha. And so the dot product is AB cosine alpha. So the length of A times the length of B cosine alpha. The cross product is AB sine alpha. And that happens to equal C, which is another vector. So we have this resultant vector, C. So this is the cross product. And so vector C is perpendicular. So you have to keep in mind that this is going to make a plane. So vector C is perpendicular to this plane. How you calculate that plane is simply by multiplying the length of A times the length of B. So we're using a different notation here to get area. And so C is a result of the cross product of A cross B, which is AB sine alpha. And area is found basically by multiplying the length of A times the length of B, as you would find the area of any parallelogram, really. So let's kind of change the notation a little bit. So up here we have ABC. Here we have A1, A2, and A3 to kind of more match what we're going to talk about in terms of reciprocal lattice. And so the area of this parallelogram now, we can calculate it from this product A1 times A2. So the length of A1 times the length of A2 gives us area. If we look at real space and reciprocal space, real space is defined by unit vectors. So we can say A1, A2, A3. Reciprocal space is defined by reciprocal lattice vectors, B1, B2, B3. You could also use the letter G. So you could say G1, G2, G3, as we've seen before, to define a reciprocal lattice vector. We have these equations now defining our reciprocal lattice vectors. So if we take this reciprocal lattice vector V1, it is the area defined by A2 and A3 divided by volume. B2 is defined by the plane made by A3 and A1, the area of the plane made by A3 and A1 divided by a volume. And B3 is the area of plane A1 and A2, or the plane made from A1 and A2 divided by a volume. Okay, so we go back A1, A2, A3. We can make different planes, okay, and they start to look like a cubic crystallographic structure if you think about it, right? So we have a plane made by A3 and A2, A3 and A2. We have a plane made by A3 and A1, so A3 and A1, and the leftover plane is A1 and A2. So this plane down here, our OG plane that we discovered, OG, original gangsta, not a line segment. Didn't mean to confuse. Anyway, question of the hour. V is volume. So where does this volume come from? Well, we've already said that the area of a parallelogram can be calculated by multiplying A1 times A2 here. All right, so now we have this plane made by A1 and A2, and we can project it along this vector A3. So we can say A3 dot this plane, A1 and A2. Okay, so we can, what does this make? So this is a volume times a height. Okay, so that's kind of cool. So, I'm sorry, this is an area, excuse me, this is an area times a height. Well, area times height equals volume. So we can rewrite V in terms of A3 dot A1, A2. Okay, so the vector A3 basically multiplied by A1 and A2. And you can't do this. Okay, this cancels out, right? These the area of this plane and this plane will cancel out. So B3 equals 1 over A3. And that's pretty awesome, actually, because this tells us that B3 really is the reciprocal of A3, okay? But the problem is you're not really allowed to divide by a vector. That's a mathematical no-no from what I've been told by my mathematical friends. So we have to look at it in a slightly different way, and we can go back to old-fashioned geometry, and we can take this plane defined by 4 points. This plane is OABC, and so that's the area of plane OABC. We can divide it now by a volume, which is the area of OABC times the height OD here. So that's our volume, okay? And so A1, A2 here is now defined by the area of OABC. Now our volume V is defined by the area of OABC multiplied by this value OD, or this height OD, and that's basically where V comes from. So OD is really equal to A3. They're both equal to the D spacing of the 0, 0, 1 plane. Well, that's quite interesting. So now we have our 0, 0, 1 plane. If you want to start thinking about it by this convention, we can say, well, B3 is 1 over D 0, 0, 1, B2 is 1 over D 0, 1, 0, and B1 is 1 over D 1, 0, 0. So if we take the dot products of these vectors, B3 dot A2 equals 0, B3 dot A1 equals 0, but B3 dot A3 equals 1. And so we kind of have these rules then we observe. BI dot AJ equals 0 when I doesn't equal J, and BI dot AJ equals 1 when I equals J. So when they're equal to one another, they're going to equal 1. When they're not equal to one another, they're going to equal 0. This equaling 0 and some other integer is very, very important because if they're equal to 0, they're perpendicular to one another. And we'll see how this comes into play when we're looking at the zone axis criterion. They're parallel to one another when they equal to 1. So this will come back to kind of get us. I shouldn't say get us. We'll revisit it again, more positive, and it's more true. We will revisit it again. All right, so now we see things that look like reciprocals. And so we're seeing that this is a reciprocal lattice vector. And so that's kind of how reciprocal space is constructed. The biggest thing to kind of take away now is this is real space and this is reciprocal space. And real space and reciprocal space are perpendicular to each other. And we can only have diffraction patterns, and this kind of comes back into play when we're indexing if our reciprocal space is perpendicular to our real space. And that's kind of the purpose of going through this kind of vector exercise. The question I just answered, what angle does reciprocal space make with real space? Well, it's 90 degrees. Why? Because they're perpendicular. Reciprocal lattice vector now, let's talk a little bit more about it. H sub HKL, or H, this is another notation for it, or G, which is the one I typically use. G is perpendicular to real HKL, or real space. G equals H times this reciprocal lattice vector plus K times this reciprocal lattice vector plus L times this reciprocal lattice vector. More succinctly, G equals 1 over D HKL, and we've kind of seen this back up here. So we could just substitute this for G, and instead of having the Miller indice here, we could just say HKL. And hopefully this makes reciprocal lattice and kind of our use of reciprocal lattice a bit understandable. So again, this is what we kind of think about. We have our limiting sphere, the radius is lambda over 2. Our K vector is noted as K with a vector, or K with a little squiggly. Reciprocal lattice vector is G. Hopefully we have a better understanding of where this construct comes from. It's just a vector construct to help us interpret diffraction patterns, basically. Etchwald sphere. So Etchwald sphere is this here. So this is really a sphere. And if you think about it, let me see if I can do it as a pen. you kind of have these beams. Hey, you didn't pin it for me. Hold on. There you go. You have beams kind of coming out, and they're kind of oblong shaped, right? And when we look at the diffraction pattern, we're actually looking at, let me change the ink here. You're looking at a slice of a sphere, okay? And so if you notice, so we're actually looking at a slice. So when we look at a diffraction pattern, we're looking at a slice of this beam, and we're looking at a cross section of a sphere. And so that's why sometimes these dots look kind of oblong. And I think more modern machines have ways to correct that. But sometimes they don't look perfectly round because we're actually looking at a section of this kind of curvy ray of, I shouldn't say light, but beam of electrons. Hey everybody, what I was trying to explain on that last slide was that when you make a diffraction pattern, you have these diffracted beams, and I guess this one could kind of be the transmitted beam, but you're taking something that would be projected in a sphere, and you're actually taking a slice of that sphere. And so you end up with dots of different diameters, and sometimes they're kind of oblong. And it's kind of analogous to taking a world map on a globe and then making a flat world map, and there's some kind of wackiness associated with that. Hopefully this clears up what I was trying to depict on the last slide. Thank you. So the Edwald sphere, it's basically telling us where constructive interference occurs. And so I said, hey, when the k vector intersects the g vector, you get diffraction. So when k is equal to g, that's where constructive interference is occurring. So let me get my mouse back. I lost it. It might be gone for good. So where you see these yellow stars, where you see these yellow stars, got my pointer back, this is where a diffraction spot's going to occur. So where these stars are where k is equal to g, where your k vector is equal to your reciprocal lattice vector. How do I manipulate? So if we're looking at a static system, okay, we're limited to what we're going to see, really, right? And we're going to limit to what we're going to diffract. So there are three ways to manipulate the Etwald sphere. So you can change the wavelength, move the sample, or manipulate the detector and or source. And this is more pertaining to XRD, but there is some crossover between the concept of electron and X-ray diffraction. So if we change the wavelength of the Etwald sphere, if we have a smaller wavelength, okay, so lambda 2 is less than lambda 1, lambda 3 is less than lambda 2, and also less than lambda 1, and lambda 4 is the smallest of them all, we're actually making our Etwald sphere bigger. It's actually kind of cool. So we can actually see more with a smaller wavelength, and hopefully that is intuitive. If it's not, think really, really hard. So, so from a crystallographic point of view, can a TEM see more than an XRD? We'll go back and look at the wavelength earlier in this presentation and compare that wavelength to 1.54 angstroms, and that'll answer your question. Move the sample. So this is where we were, and this is where we are. So you can move your sample, and we're actually changing which dots interact with the sphere somewhat. So moving the sample is another way to manipulate your Etwald sphere and change what you're seeing or diffracting. And moving the sample is how Lau rotating crystal works, and we talked a little bit about rotating crystal before, where you spin the crystal on an axis and you have that photographic paper. So you can refer back to X-ray diffraction if you have forgotten what I'm talking about. All right, so the third way we talked about for manipulating the Etwald sphere is moving the source or the detector, and you really can't do that on a TEM. The column is pretty static, and your recording plane is also pretty static. And in fact, I shouldn't say pretty static, it is static. So this is actually more for XRD. And so this is actually happening when you run an XRD. You're moving typically the source and the detector. But this is a depiction of the effect of the Etwald sphere. So each of these colored circles is one position condition. And I think we've talked about quite a bit in this lecture. And so I think this is a good place to stop. If you have any questions, feel free to email me, and hopefully this has been informative to you. Thank you very much. Oh my! It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.